What's up, everyone? Today we're going to talk about exponential functions. All right, so an exponential function has to have your variable in the exponent. That's what makes it an exponential function, that your variable x, in this case, is within the exponent. Also, to note that a, the value up front, can't be 0, which makes sense because then you just have y equals 0. Your b is known as the base, and it has to be a positive real number. That means this value can't be negative, but it can be a whole number, it can be a fraction, it can be a decimal. It just can't also be 1. That's the only other stipulation. So no negatives, and it can't be 1. It can't be 1 because if I do 1 to the x, or 1 to any variable or any value, I'm just going to get a straight line. 1 raised to anything is just 1. So that's why we're not including 1. All right, so we have two major types of exponential graphs. It can be a growth, as seen over here, or it can be a decay, like you see over here. So in order for an exponential curve to be a growth, that means that your b value, that base, has to be greater than 1. In order to be considered an exponential decay, like we have over here, that base has to be between 0 and 1. So any kind of fraction or decimal between 0 and 1 is what we're looking for to get this decrease in the graph. Both graphs have a domain of all real numbers, and both parent graphs also have a y-intercept, as you can see here, of 0, 1. So I'm specifying that both parent graphs, meaning these haven't been transformed at all, have a y-intercept at 0, 1, because based on or depending on different transformations that you'll have, that could change your y-intercept. What both graphs also have, as is an asymptote. So an asymptote, remember, is an invisible boundary line. You can have vertical or you can have horizontal, but it's an invisible boundary line that the graph can't and won't cross or touch. So in both of these cases, in all exponential graph cases, you have horizontal asymptotes, which means y equals, because it's passing through the y-axis. And your parent function asymptote is at y equals 0. If you notice, both of these graphs, if I draw in a dashed line at y equals 0, this graph gets really close and it looks like it touches, but it technically doesn't. And same thing over here. Again, just like your y-intercept based on transformations that may happen, that asymptote can change, which we'll talk about in a couple slides. Your range is also dependent on your asymptote. If you notice for both graphs, my graph is above or greater than my asymptote. And so I could say that my range is y is greater than 0, or if I prefer interval notation, from 0 to infinity. So note that we're not including the asymptote. You can never include the asymptote in your range in this case, just because, again, it's not going to touch the asymptote at all. So we're strictly greater than the asymptote, or using parentheses, meaning we're not including it. Right, so on this page, we're asked to do this without graphing. We know we can if we need to, right? But we should be able to do it without graphing. We're determining whether the function represents a growth or a decay. So remember, a growth means that b has to be greater than 1. So if I look at my b's here, the number being raised to the x, number 2 and number 3 both have a base that's greater than 1. So these are both growths. Versus a decay is when b is between 0 and 1. So if I look at number 1 and if I look at number 4, both of those have decimals that are between 0 and 1. So these are both decays. All right, so on this slide, we're asked to use our GDC, aka our calculator, to sketch all 4 graphs at the same time. And if you do that, you get something that looks like this, and I tried to color code. So they're saying that all of these are part of this family, b to the x, where we already know b is our base. But note that B is not considered a transformation. Yes, it does change some of the shapes of the graphs or whether it's a growth or a decay, but it's not an actual transformation. So just be aware of that. The differences between when my base is greater than 1 and when my base is between 0 and 1. Let's talk about greater than 1 first. When b is greater than 1, so I'm looking at 2 to the x and 10 to the x, similar to what we just saw, that both of those increase. Those graphs increase or it represents a growth. So I'm going to say this is for when it's a growth and the graph increases. When b is between 0 and 1, so we're looking at 1/3 of the x and 0.5 to the x. So looking at both of those graphs, remember that when your base is between 0 and 1, it automatically represents a decay, which we can see here. And we can also say that both of those graphs decrease over time. So this represents a decay, and the graph decreases. All right, in part 2, we're asked to graph all 3 of these at the same time. We get something that looks like this, again, color coding. So they're saying that these are part of the family b to the x plus d, where d is a constant. Note that d is not in the exponent. It's next to that b to the x. Looking at the differences between when d is greater than 0 and d is less than 0. So if we look at d is greater than 0 first, meaning that, looking at this pink graph, it took the original 2 to the x and it shifted it up 1 step. So when d is greater than 0, the graph will shift up. When d is less than 0, so looking at this -3, or this red graph over here, it took that original 2 to the x graph and it shifted it down by 3. So I would say that when d is less than 0, it shifts the graphs. So I would say when d is less than 0, it's a vertical shift down. Final question on here is, how does d affect the horizontal asymptote? So if you notice with all 3 graphs, all 3 look to have different horizontal asymptotes. We know that 2 to the x, because we just saw something similar, has a horizontal asymptote at y equals 0. If you look at my pink graph, 2 to the x plus 1, it looks like my horizontal asymptote shifted up by 1. And if you look at the 2 to the x minus 3 graph, it looks like my horizontal asymptote shifted down by 3. So all of that to say that d changes where the horizontal asymptote is. If I take a horizontal line and I move it up or down, it's going to change where it is. So you can say just d moves the horizontal asymptote. We could also just say d is the horizontal asymptote. All right, part 3, using our graphic display calculator to graph all 4 functions at the same time. We have something similar to this, not a great graph, but you get the idea. All of these are part of the family y equals a times b to the x, where a is any constant. So a can be positive, it can be negative, it can be a whole number, it can be a fraction or decimal. It has lots of different options. So, and we're going to describe all of them in here. So first up, when a is less than 0, so that means that a is negative. We only have one of those in this pink graph. So comparing that pink graph to my original blue graph, you can see that it's been reflected over the x-axis. Next up, when the absolute value of a is greater than 1, we put those absolute value signs in there just to make sure that you're looking at just the number. The negative sign is its own thing. We just talked about it. So just looking at the number itself. So when that number is greater than 1, so looking at like this green graph when we had a equaling 4, if you notice it's a little bit steeper, or it's a little bit stretched vertically. So any number that is out front and being multiplied to the base, that's going to cause a vertical stretch. Because I'm taking the graph and I'm stretching and pulling it vertically. Finally, when a is, the absolute value of a is between 0 and 1, again, so we're looking at just the number of a, not the sign of it. And now it's saying it's between 0 and 1, so it's a fraction or decimal, similar to what we have in this orange graph. You can see it's been a little bit squished down, right? It's been compressed vertically. So I'm going to say vertical compression. I'm using vertical here just because it might be sparking something in your brain from Algebra 2 that out front or in the beginning of an equation, if there's a number that's multiplied to your parent function, that's automatically a vertical change. There are such things as horizontal stretches and compressions. We're just not going to talk about them in this capacity. And finally, in piece number 4, we're asked to graph these 3 graphs at the same time, or these 3 functions at the same time. Note that this time the additions and subtractions are in the exponent with the x, and that does make a difference. And we get something that looks like this. Again, not a great depiction, but I'm trying to emphasize the changes. So we have the family of b to the x minus c, and I'm emphasizing that the base transformation implies minus c, where c is a constant. So when we start to describe the differences in the graphs when c is greater than 0 and when c is less than 0, they're looking at just this value. They are not including the minus with that. So when we're looking at when c is greater than 0, we're actually looking at this kind of graph, because just like in this example, both of them have an x minus, and that value itself that you're subtracting is what we're looking at. So with our red graph, when c is greater than 0, it moved to the right. If you notice the difference between the blue graph and our red graph, when c is greater than 0, it's a horizontal shift to the right. Versus when c is less than 0. So what that means is with this graph, I could rewrite that as x minus a negative 1. That's what they're talking about, that c is less than 0, because now this negative 1 is now negative, so it's less than 1. So we're looking at this pink graph, and you can tell that it's been shifted to the left by 1. So anytime c is less than 0, it shifts to the left. Finally, how does c affect the horizontal asymptote? If you notice, all of these look like they have the same horizontal asymptote, which makes sense if you think about it. If you have a horizontal line that you're shifting left or right, it's not moving at all. Unlike when we moved it up and down, that moves the horizontal line, but moving it left or right doesn't change it at all. So I'm just going to say it doesn't. All right, so bringing it all together, we have all those letters that we just saw all in one equation or in one function. So A and B, these two up front, control a lot. I'm going to say, I don't know if it's a word, but I'm going to say they control the steepness or the grade of the graph, right? How fast it increases or decreases. It also controls whether the curve increases or decreases. So it controls, we've seen with B, especially, right, whether it's a growth or a decay, where you can say that it increases or decreases. C, in the exponent, we know controls the horizontal position of the curve, while D, not in the exponent, controls the vertical position. Y equals D, remember that vertical change, is the equation of the horizontal asymptote. We had already stated that the domain of any exponential function or all exponential functions is all real numbers. And the range of all exponential functions depends on 2 things. So it depends on, number 1, the sign of A, because we had seen that if it's negative, it can reflect it over the x-axis, or if it's positive, it's on top of the x-axis. So it depends on the sign of A, but it also depends on the value of D. So we had said D is the horizontal asymptote, and that will change the range as well. So finally, a couple of practice problems. We're asked to do 4 different things here. Identify the transformations, state the equation of the asymptote, the domain, and the range of each of these functions. So first up with number 1, identifying my transformations. I have that 2 out front, which remember we said when when a is greater than 1, it will stretch the graph vertically. So I'm going to say vertical stretch by 2. I have a 3, but remember my base is not a transformation, so I'm not going to say anything about that 3. But I do have a -5 outside of the exponent. So that -5, since it's not in the exponent, is a vertical shift down, because it's negative, by 5. My equation of the asymptote, remember all exponential functions have a horizontal asymptote, so all of these equations should start with the y equals, because it's going through the y-axis. And we had said whatever that transformation, that vertical shift is, or whatever this d is, that's what your horizontal asymptote is. So in this case, it's a -5. My domain, we said, is always all real numbers. And my range. To find out your range, it might be helpful to graph this function just so you can get a feel for what the graph actually looks like if you're a visual person especially. I'm going to do a quick sketch of it over here. I know it's been stretched by 2, so it'll be a little thinner than normal, or a little bit taller and skinnier than normal. But also, more importantly, it's been shifted down by 5. So instead of looking like here, it's going to be down here with that asymptote at -5. So what that tells me for my range is, if I wanted to write it using inequalities, y is greater than my asymptote at -5. Remember, you can't include your asymptotes, so I'm not putting the equal to here. I could also say, for interval notation, that I'm going from -5 up to positive infinity. So from the asymptote and up. Number 2, I also have 2 transformations. One is the negative out front. We'll reflect it over the x-axis. 2, if you notice, I have a -2. This time it's in the exponent, though. So note the difference between the font size between number 1 and number 2. They don't always put parentheses around the exponent. You're more than welcome to add them in yourself, but just make note that you do need to pay careful attention to the font size. This guy is in the exponent, so that means it's a horizontal shift. Horizontal shifts are always the opposite of what you think, so since it's a -2, it's going to go to the right by 2. My asymptote, again, always a horizontal asymptote for exponential functions, so I know it's going to start with a y equals. And if you're looking at this and saying, well, there's no d, so that means I don't have one. There's always a horizontal asymptote with every exponential function. So if there's not a d written, you're more than welcome to write in a +0, since we just don't normally write that, but it can help you identify that, oh, okay, my horizontal asymptote is just at 0. So if there's nothing written there, you can either write that in, or just remember that it always starts at y equals 0. We know our domain is always all real numbers. And again, for my range, I'm going to go ahead and do a quick sketch of this, or you're more than welcome to graph it in your calculator. All right, so I know normally my graph would look like this because it's an exponential growth because of my base, but because again it's been reflected over the x-axis, we'll be down here now. And it's shifted to the right a little bit, which it's kind of hard to sketch that in, but something like this. So that means my range, I can draw in my asymptote. My range, if I'm doing inequalities, now I am less than my asymptote. So my range could be y is less than that asymptote of 0. Or for interval notation, I'm going from the bottom of my graph, which since it's going down, I'm going to go from -infinity up to the top of my graph of 0. That's it. So that makes exponential functions a little bit more clear.